pleased to introduce Joxan Jaffar, who's the chair of the computer science department at Singapore National University. He's going to be talking to us about open constraint programming. Everybody that took 505 has probably encountered Joxan's work. He was the main architect of the COPR language. He actually graduated with a PhD from Monash University in Australia, spent some years at IBM Research before going to Singapore. So Joxan.
Thanks very much, Alan. Can everybody hear me? Thank you very much. I'm delighted to be here. I understand it's very atypical weather for you today, but I've come from 3 weeks in the Northeast, so I'm sort of in a little bit of euphoria now. My talk today is going to be on open constraint programming. This is going to be a little informal presentation of some ideas in concurrent programming that we have been developing, two colleagues and I, over the past couple of years or so. And the general idea is as follows. We want to do concurrent programming with shared memory, but in particular, where the shared memory has very high structure. So for example, you might want to share a logical theory, a set of formulas, or you might want to share a database with high structure, an object-oriented database, or in the examples that I will show later on, constraint databases. And I will use some examples to show why today the problem is becoming even more relevant, in particular with the advent of the web. So that's one major component of the work, that the common store, the shared store in concurrent programming is highly structured. The second main aspect of this work is that we would like the concurrent processes, we would like the system to be open, and so you have a lot of freedom to choose to write concurrent processes in the language of your choice. So in particular, you can use any certain language, but of course this raises the problem of how do you communicate with this store. And what I would argue is that what you need is a very specialized reactive programming framework in which you can embed into your favorite concurrent process or agent. So these are the two components that I would like to tell you a little bit about today. As I said, the talk is somewhat informal and descriptive, mainly to try and persuade people that there is indeed an interesting programming methodology that requires this kind of thing. First, just a little bit of related work on concurrent programming in general. Coming from my background, the people who work in concurrent programming generally work on process calculi for the formal presentation of concurrent frameworks. So a canonical example of this is the pi calculus. Over here, people have been very concerned about synchronization and sort of using minimal formalism to define concurrency. There is a little focus on general notions of reactivity, and certainly there is very little focus on a shared store in particular, and in particular a big shared store. On reactive programming per se, there's a class of reactive programming languages. So some canonical examples are Astral, some two-dimensional ones like state charts and so on, whose purpose is to talk about reaction. Over here, the kind of concurrency is focused on signals that somehow are received from the environment, and you want to respond to these signals in a timely way. You don't particularly care about the state of affairs before or about the collection of signals received so far, so sort of an instantaneous kind of response. So that's the focus there. It certainly is not, this class of work is not suitable for general purpose concurrent programming, and once again, certainly no database considerations at all. Slightly closer to home is the area of coordination languages. So canonical examples here are the system called Linda and the Blackboard architecture, where basically you want to perform concurrent programming on some kind of shared memory which has some kind of structure. Typically, traditionally these structures are traditional data structures, arrays, lists, sets, things like that. So for example, in Linda, you have a basic notion of a set of tuples, and you perform, and concurrent processes share this set of tuples. Synchronization is defined very simply by a single operation on a tuple, namely on a concept of tuple matching. So here you already have some kind of structure. There are some arguments why this is good for general programming, but Blackboard and coordination languages do not really address reactivity in a sufficiently general form, and also here they don't address the notion of properties of the store as a whole, that you don't really talk about the set of all tuples as a whole in conjunction with the reacting processes. So for example, database issues such as concurrency control are of not great interest here. The closest area, I think, and is natural for someone like me coming from constraint programming, is the area of concurrent constraint programming. Over here, like in Linda, you have a shared store, except that the store is described by a set of formulas, a set of logical formulas. So there is a further notion of the further level of declarativeness in this store. Here, concurrent constraint programming, which appeared a little bit later than regular sequential constraint programming, focused on the use of a specific programming language, a rule-based programming language with a specific form of concurrency. It is in fact, is an opposing point to mine about open programming, which I would like to focus on a little bit more. Even though Alan mentioned a course in which you guys took constraint programming, I thought maybe it's worthwhile for me to just spend a minute or two telling you a little bit about constraint programming, so where we are coming from. The general idea behind constraint programming revolves around the idea of a common store for everybody, sequential or concurrent. So over on the left, you see a store there with two formulas, and that will represent for the moment information that we are sharing. It talks about three variables, x, y, and z, and it talks about specific properties that we all understand, whose semantics we all understand. There is a basic operation of being able to add to the store. So in CCP, there's a notion of tell C, where C is just another constraint like that. And that operation simply augments the store with one more constraint, providing the set of constraints remains consistent. Otherwise, you have some kind of failure. More importantly, you also have a logical condition such as ask of C over here. And the idea here is that this is a logical condition which asks if C is implied by the store. Okay, so nothing surprising there about the logical condition, except that the operational semantics is defined such that there is blocking if and when that condition is not true. So you have a notion of block. If this ask appears in some program, then at that point, execution is suspended until the condition of interest becomes true. So once you have this notion of blocking, you do have general purpose concurrent programming, at least at the level of CCP. In an earlier life on the right-hand side, CCP has had a modest amount of success in the incarnation known as concurrent logic programming, where stream-based concurrency was used in a big way. Now, constraint programming has had quite a bit of success. Constraint programming in general. Of course, the primary one is that when you write something down representing the elements of the problem you're working on, a main facet is that it is declarative. But more importantly, what you see is not what you get. Okay? So the information represented inside a constraint store is supported by a powerful reasoning algorithm which can tell you many more things than just the constraint sitting there can tell you. Okay? So these things you understand from general basic constraint programming. And these ideas have been very successful. And today I would say the biggest success have come in the industrial applications for optimization problems in resource allocation, scheduling, things like that. A lot of work, of course, in our community has been done embedding this kind of intuition into programming languages so that you can use them and program them properly. However, if you look at the successful applications, you will find that the really interesting or the really important concepts that have been used to make those successes in the applications are the use of the constraints themselves and the various techniques in combining, reasoning about constraints, etc. Not so much how these operations are realized within the programming language. Another area of reasonable success for constraint programming, apart from combinatorial problems, is the area of model-based reasoning. So at the base of your problem, you have some complicated typical physical structure which has many relationships which are useful to be captured by constraints, and you want to perform reasoning on this. Once again, if you look carefully at these applications, the use of specific constraints and the control of how the newly dynamically created constraints are generated is the key to the solution of the problem, not so much the programming language itself. So what I'm trying to say in this couple of transparencies is that there's a lot of strength in constraint programming, but not necessarily in the programming languages that have embedded the notion in the past. So what I want to talk about today, as I said informally, is the following. I'll talk about my framework in two main parts. One part, which I shall just call a constraint server here, and by the way, when I mention constraint store, shared memory, constraint server, and database, they mean exactly the same thing. So I'll talk about why we would want to have better databases. After all, there is some folklore that there's nothing left to do in databases. Okay? And the second part is the accompanying programming part. Given an open system where people can come in with programs written in any language, how can we possibly express all the important constraint as well as concurrency aspects in order to work with the store? How do we do this? So I'm going to call this programming language a reactor system, and I will tell you a little bit about how we define reactors. And I will probably not talk about implementation models and why there is some plausible reason all these things can be implemented. Okay? So I'll refer to some papers for the more detailed information. Okay, let me jump straight into an example. So let me just start by giving you two examples of a server. This is a traditional constraint programming kind of examples. Since you all have seen CLPR, you will know about its constraint store. The constraint store of CLPR, formally speaking, is a set of real linear formulas. And in the context of a constraint database that I'm talking about, you could think of the following as reasonable operations. Okay, an operation on a database could be a tell operation, so the operation of adding a constraint to the store. You could have a variant of tell like soft tell. Soft tell adds a constraint to the store but does nothing if that addition would create an inconsistency. Okay. You also, as in CCP in the example before, you can have an operation of ask constraint. But the semantics of this is that this operation returns true just in case the constraint is entailed by the store. However, I'm only describing a server and not its reactive behavior. So the ask constraint over here or the ask operation over here is purely passive. Okay, it is true or it is false. There is no notion of blocking that I'm talking about at this stage. So that's a very simple example of a server, not a very interesting one since you've already seen it before in some sense. A slightly more interesting example of a server is a constraint database. So here, think of a constraint database as a Prolog program or any rule-based program where what we are sharing is not the constraints as in the previous example, but the program itself. So the program itself is the entity that we are sharing. And if you do so, you have this database, which is a single program. What would be reasonable operations on a rule-based program? Well, obviously, the operations of inserting and deleting rules would be one for you to change the program from one program to another. But of course, it's no use if you cannot ask any question of the program. Just sticking to a Prolog framework for the moment, the easiest and most standard way of getting information from a rule-based or Prolog program is to run a query or a goal. So in this example server, I define that the operation goal G is a query, and it returns answers in the expected way, and I'll talk more about that in a minute. So just a trivial example to set this example a little bit more concretely is the following. On the left-hand side, I have a little database with 4 rules over there. What is it we're sharing when we say we share that server or that constraint store? Just like in any programming language or non-syntax based programming language, what we are in fact sharing is the semantics of that program, not just the rules. Okay? So in other words, if I look at the relation P over here and just perform some intuitive reasoning, I can see that the information carried by this program is P of A. That means the proposition P of A is true of that particular program. Now, if my concurrent process eventually came and performed an operation of assert upon this program, thus getting a slightly extended program, notice that the meaning of the program now changes, and the meaning of the relation P now has 2 propositions, not 1 over there. This general pattern is what I'd like you to see, because I would like to introduce more sophisticated examples later on. Okay? So this is a much more interesting example of a constraint store. It's just spoken of in a different language. The ideas are the same. In a constraint store, it's very powerful because in a succinct and finite way, you can represent an infinity of information. So it's exactly the same over here, right? Okay. So before I go into deeper examples of the server, I'm going to shift gears for a few minutes and now talk about the other component. So as I mentioned before, if you want an open system, you would have to define now the communication or concurrency primitives in order that your favorite program can be adorned to work with a shared store. Okay? In general, I'm going to call this notion a reactor. So a reactor is nothing more than a reactive program fragment intended to be embeddable in programs. And as I mentioned before, there are some examples of reactive programming formalisms already, but I also mentioned why they are not suitable for what we want. Okay. So I'm just going to go through some informal examples of what reactors could look like and what do you want in a reactor. Well, first and foremost, you must be able to perform a basic operation delta upon the database. At this point, delta is not of interest. I've showed you an example of a Prolog database. Delta is assert, retract, or ask a query. So that's not very interesting. You clearly must allow the primitive update operations of the database within your reactors, okay? So that you can change. Then the most basic element, the most basic concept you could implement in order to have concurrency is a notion of blocking. So for those operations delta upon which there is a notion of true or false, you could define a reactor called wait of delta, which performs much like the ask of CCP, namely that we have a blocking condition over here until such time the update delta will be true. Okay? So the delta, for example, could be ask x equals 5 or something. That would be a reasonable thing. So up to this point, I can go back to some related work such as Linda and remind you that in Linda, they also provide something like this, a basic primitive mechanism based on tuples. You can talk about a tuple. That tuple may or may not match some tuples in the database, and upon that condition, you have synchronization, and from there, general purpose concurrent programming. However, this is often not enough for, in order to be a rich programming framework. So just to carry on this direction a little bit further, here's another idea of a slightly more complicated reactor. So here's a reactor with 2 deltas in it, delta, delta prime, and an arrow in between. So this concept is very familiar in declarative concurrent programming languages. The idea is as follows. This reactor blocks until the first update delta is true. If and when it becomes true, it performs the second update delta prime. Very intuitive. Now, again, this appears in CCP in some form. It is also important in concurrency, in programming concurrency, to be able to specify how long it takes for delta prime to execute if delta is true. So you could include with this definition of a reactor a notion of atomicity. You may want it, or you may not want it, or you may want both. Okay? So that notion is important. So for example, if delta spoke about the stock price of a company in a certain nice range, and delta prime spoke of buying the stock, you would like to buy the stock at the price you expected, right? That sort of thing. Right. So a generalization of this idea, a generalization of this idea is the so-called notion of Dijkstras God, where you don't have one, but any finite number of such arrowed constructs. And over here, the general idea is that this construct is blocked until at least one of the delta i's on the left-hand side is true. If and when that happens, then a non-deterministic choice is made. This is an important step. Okay, you have a non-deterministic choice is made. Say delta I is chosen, and the corresponding action delta I prime is executed. Once again, just like the previous example, you may want or not want atomicity between the test and the action. Okay? In fact, you may want it atomic in some cases and non-atomic in some other cases. So you might want, for example, to use two different kinds of arrows. So up to this level, this is already discussing concurrency constructs that is more general than you can get in concurrent constraint programming. Yes, sir?
When you say atomicity, do you mean atomicity with respect to the state of the store, common store?
Yes. Yes. Atomicity is a loaded term. Depends on a timing model. For the purpose of this talk, atomicity means happens in zero time. Okay? Nothing else happens in between. Everything takes time. All right. All right. Here's an important reactor for us, and this does not appear in the literature. Because I've been talking about rule-based databases, it makes sense to have a reactor that is based upon the queries you can ask of those databases. So if your database is a set of rules, I would like to define a reactor that says, if and when this goal, and in Prolog it's typical to write a goal with a number of atoms A1 to AN. It's not important that you know what they are. It's just a way of you asking a question. If and when that goal A1 to AN is true, then execute excuse me, the update delta. Now, in general, a rule-based database returns more than one answer for each query. It can be an infinite number of answers. So you could specify that in case there is a finite number of answers, let's say k answers to that question, A1 to AN, then typically there is a constructive way in which the answers are returned. In logic programming terminology, is typically written as θ1 to θk, and this specifies the various specializations of the operation delta that you can perform. Then I could define that the semantics of this reactor is that the k operations delta θ1 all the way to delta θk are executed concurrently. Okay? So you ask a question, you get k answers, you execute the k resultants concurrently. Right? So once again, I'll show you examples later. So okay. I'm ready now to tell you the framework in its full generality, or its generality today anyway. So this is the abstract definition of the reactor framework we're proposing. A reactor may be, at its base level, an update. It may be of the form event condition, so the next two arrows over there, whereby the first one allows only a primitive update. So not a completely general reactor here on the right-hand side. So the idea here is that if the condition C is true, so this C and this U should be thought of as the deltas I was talking about before, except that we just say C is a passive update. It doesn't change the database, and U is an arbitrary update. And this double arrow is defined for atomic action, whereas the other arrow is non-atomic. If it is non-atomic, you may write a completely general reactor over there. In this calculus, we have, in this ampersand over here, the normal interleaving. Okay, so nothing different from the pi calculus, for example. I mentioned non-deterministic choice before. In fact, it's important to have actually more than one kind of choice. And at the moment, we have a couple of kinds of choice. I'll explain in a minute. We have sequencing, nothing surprising there. We have a notion of atomic transaction. So this has to do with atomicity, and I'll explain that again in a second. And finally, we have this replication operator. So this is very much like the pi calculus for those of you who know, and basically allows you a form of iteration. It's better than iteration, but it at least includes iteration. So let me explain a little bit what they mean. Okay. So for the very first one, you notice that the only new thing is this little subscript n on the arrow here, and here we would like to be able to specify how many answers you're interested in, and then perform the appropriate concurrent execution of the updates. Everything here happens atomically. That's for the very first one. For the second one, there's basically non-atomic updates when C becomes true. Now notice the next two constructs, early choice and late choice. In early choice, the idea is as follows. The moment you can say that one of the two reactors, R1, R2, makes some progress, this needs to be formalized, and it can be seen from our paper. But the basic idea is that if it touches the store in any way and makes a difference, then you may kill the other reactor, which of course has no effect at this time. So this is early choice. It's also important to have late choice, whereby you again want only one of them. You don't know which one a priori, but you would like to have in the late choice the one that has finished. So the result of executing R1 choice R2 is always one of them, not both. But the question is, when do you terminate the alternative? Okay. So this is, has some similarity between the comparison of eager and lazy languages. Okay. So it's more declarative to have the late choice, but it's also more difficult to implement. Okay. However, one difference for us is that we will define that any effects of any reactor, both of them remain. So even if one finishes and you abort the second, any effects of the second remain. Okay, so we have some sort of persistence over here. Replication is sort of more of the same. I'll save time and not go into that. Let me just talk briefly about transactions. This is the most problematic of our programming constructs. Putting a square bracket around a reactor makes it a transaction. The idea is that when you make something a transaction, it runs on a separate machine with a copy of the database, its own copy of the database. It does what it does in isolation. Okay? So any changes to the database during the time you are executing R is not visible. Any effects of R is not visible outside. Okay? So here in our operational semantics, at some stage you have to make the operation of R visible to the rest of the world. And so we define a notion of smash so that the result of executing R on a separate machine and the main thread, which is executing the other parts, can be merged together. This merge operation is a fairly complex operation. It is not unfamiliar to database people. In our framework, it's a parameter. We simply require that you obtain the desired serialized semantics. Okay? So in practice, such transactions are heavily restricted to reasonable applications because clearly it's something very difficult to implement. In the database community, this phenomenon appears in two different schools. One school, a more traditional school that uses locks. So you implement this by allowing everybody to proceed, but you lock any aspect of the database that you do not want anybody else to operate on while you are there. Another school is a school that work on optimistic recovery or optimistic databases, where you go ahead and do whatever changes you want anyway, and you hope that nothing goes wrong. If something goes wrong, you roll back. Okay? And that's also reasonable. That's something more familiar to people in parallel logic program, where you just do things and you roll back if it doesn't work. And in our paper, we talk a little bit more about examples here. Okay, so that's kind of heavy going, I know. So let's go to examples. Okay, here are 3 examples. Very simple examples. Take the first one. The first one has a condition called time. We will assume that you have a database in which there is a predicate time, and the value of that predicate is exactly the time now. Okay, and somebody changes the time. I want to write an alarm clock, meaning that if t, the current time, is between some desired hours x and y, and some condition is true, that condition signals the alarm that I'm interested in. I'm not really talking about C in this example. I just assume there's a condition C. Then you might do some alarm operations such as delta. So the point is I just wanted to show you what's on the left-hand side of the arrow over there. Very simple alarm clock. Okay? So this reactor can be launched by your Java program anytime if you wanted to watch a database once. If you wanted to watch it all the time, then it's up to you to launch this reactor as many times as you like, right? Okay. The second example exemplifies the notion of timeout. You must agree this is a very common thing. In concurrent programming, it's very reasonable that you want to do something unless it takes too long, right? So when you're ready to do that thing, let's call that condition time t. So once again, this will just succeed with the appropriate value of time. Okay? Then you can do one of 2 things. Either you can do R or you can quit. Right? You can quit if this condition, this is a late choice. Right? This is a late choice. So you can quit if this condition becomes true. And if you just stare at this condition for 2 seconds, you'll see that all it says is that the time is very late, and then you do nothing. This is just this shriek means nothing in reactor language. So if it's too late, it's possible R will be just killed, and that's it. Okay.
What's the subscript 1 of the
That's just to say I want one answer. Yeah, it's a little bit unnecessary for this example. You need the answer because there is one answer for T. You need to carry T into the body of the program. Yes, sir?
If R has side effects, then
Yes.
you would have those side effects happen before you kill it. You don't undo them. Is that
Right. Absolutely. Yep, so Alan has caught me out here that if there are any side effects that are undesirable, tough luck. Yeah. Yeah.
Why is there no non-side affecting version of late choice?
Because it's my database collaborator. It's not reasonable to have it in most frameworks. It's just not reasonable to backtrack arbitrarily, right? Because everything you do has to be speculative. It's just not reasonable. Yeah.
But if you enclose that R inside square brackets, would that make it atomic? And
It's not exactly the same. It's not exactly the same because while you enclose it, it cannot see what's happening outside, right? So it's not exactly the same, but you can do that. But as I said, you will not generally allow arbitrary things to be transactions. In an instance of this calculus, you would be very reasonable. And I can show you some reasonable things later on. Okay, so just switching this example around. Now, I want to execute R. I don't care how long it takes, but it has to start on time. So you can see that the 2 reactors are very similar. All I've done is change from late choice to early choice over there, right? And it's the same sort of idea, but it's a very different thing we're talking about now, right? So fairly complex concurrent operations can be specified relatively trivially once you have the right constructs. Okay? If I have to backtrack now, it will be problematic. I have a non-deterministic choice here. Yeah. Okay, some example that is a bit mundane, more mundane. And I have a little typo here which I'll fix on the fly. Okay, the idea is that I have 2 predicates in my database of interest, an order predicate which is an order from a customer of some number of widgets. There are only one kind of widgets in the world. And I have an inventory predicate which tells me at different locations, at each location, how many of those widgets I have. I expect this number to change over time because those guys will keep changing this without, without you seeing it. But as a seller, I would be interested in this sort of reactor. Whenever I receive an order N, and I have, so this is the first line, and I have enough inventory, sell it. So I just update my inventory. The funny symbol tensor just says update, so change the value to this value. So I just fill the order becomes 0, and of course I decrease my inventory appropriately. A choice, in this case it is mistakenly using an early choice, is that I replicate. So replicate, just think of it as having an infinite number of copies. Okay, I have an infinite number of copies, but I can interrupt this when the termination condition is true. So I have as many copies as I want of this reactor. Each copy is listening to the fact that there is an order N. It's listening to the fact that somebody, inventory WM, so some location W different from headquarters, has some inventory, and it is going to ship me some of that. It may not be enough. It may or may not be enough, but it's going to ship me some. And I assume some other part of the program deals with the operation ship to make sure it gets to headquarters. You can see here, in this framework here, you can believe, I think, very easily, that the order will be filled if, at some stage, if the various locations have enough. Now I mentioned that I mistakenly used here an early commit that will commit you to a remote strategy or a local strategy up front when what you want is a late commit over here, so that you can do some remote and then apply a local strategy as well. So this is more down-to-earth sort of thing. This sort of databases exist a dime a dozen, right? And very easily I can give you a selling strategy. And of course I can make it much more complicated than this. All right. So just briefly, so far I've just shown you reactors as examples. Here I just want to briefly change back to an intuition of the store being a constraint store as per normal, just to show you now reactors embedded in a C-like program. Okay? So imagine for the moment I have a store which has got integer constraints over some n variables x1 to xn. The domain of x1 to xn is 0, 1, and it states some very complicated constraint whose satisfiability is unknown, say, some very, very difficult constraint. Okay, there are plenty of those. Okay, and over here, in this C program, all I'm doing is use two reactors. One reactor which augments the store for each xi, the value of 0 or 1. Okay, and a reactor which removes the constraint. So I put in the constraint, I remove the constraint. So this is not exactly the same as constraint programming as you know, because I'm allowed to retract that constraint. Okay? So if you had used CLPR, you would do it in the programming language itself by backtracking. Okay? But here I do it forcefully in C. And it's not hard to see that this is exactly an implementation of chronological backtracking in constraint solving. Okay? So I can do this. But the main point was to show you that I can do basically embed reactors inside traditional programming languages. Okay. All right. So far, I've talked about the general ideas of using a server with high structure. I talked about the database of a ruler program, and I basically finished talking about this reactive programming framework, giving you an overview, trying to justify why such a general purpose programming framework is needed. I believe that it is needed for all kinds of reactive programming, regardless of whether the server is a highly structured one or not. Okay? The concept that I've talked about there makes sense, I think, under any shared structure, as long as there's a notion of some shared memory. However, now I want to talk about the server for a little while, and I want to talk about the issue of what having high structure means? I want to talk about thin and fat clients. I think of a server that contains very little information as something for which your clients has to be fat, and servers which contain a lot of information, something where the server is fat. Now, in constraint programming, the intuition is always that the server is very fat, because a lot of the reasoning and a lot of the reasons why you get the desired answer is because of operations within the solver. You have controlled it from outside, but a lot of the work happens inside that solver. That basic motivation, I think, can be used in the same way in OCP. So once again, in constraint solvers, the shared store is of great use, not only because it has a declarative reading, as I said before, but there exist powerful engines for reasoning about those formulas. That's point number one. In OCP, and in some of the examples I'm about to show you now, we have exactly the same advantages. But one more, we can program the server. So it's not only declarative, but I can also embed a reasonable notion of operational semantics to it, which is useful. So let me give you some examples. Okay. Take, for example, a bidding situation. So here's an application. I wish to implement a bidding situation. I invented this auction, by the way. It's not any real auction. The idea is that it's an open auction. Anybody can bid any amount you like. The winner is the guy at closing time who bids highest, but the price you pay is the second highest bid. Okay? Very reasonable auction. Okay? It's very efficient auction because apparently you try not to bid so much if you're happy with the price. Okay, so I've given you this. Go implement this. So you need a concurrent system. You need a little database because when people bid, you have to remember who bid what. You have to remember what the highest price is. It's very trivial, but nevertheless, it's a concurrent programming application. And you have no idea who's coming in to bid. Anybody can bid well. Anybody who has an ID can bid. Okay? So in this database, I have a predicate called bid. That's the entry point. So you put in your bid. Furthermore, I will also allow the predicate's second highest bid to be visible. That's the only thing that's visible. So an external agent may inspect the second highest price. He knows that's the price so far. That's the going price so far. And you can bid, of course, some number higher than that, whatever you like. I can bid any number of times I want. The last predicate terminate auction clearly is for me, the auctioneer. I will launch that reactor. Nobody else will be allowed to. Very simple. Now, this code looks a bit weird for some people not familiar with constraint databases. Basically, it says that if you bid n, and n is bigger than your previous bid, then I'm going to change my record. So minus is an retract, plus is an assert. Okay, just using database brevity. Okay, and then I update the price, and then I update the price in the obvious way, depending on your price. If your price is higher than the second price, then sort of thing. If your price is in between the second highest price and the top price, then the second highest price changes. Okay, really trivial logic. But the point is, this database represents very clearly what I mean by the database. I do have a database of bids. I do have a database that's telling me what the highest price is, second highest price. All the necessary information is there very clearly. Also, it was programmable. So it took me 5 minutes to write this application. Okay? And it works, completely open. All right? So all you need to do is bid. Here's another example. So here's a server that's intending to be a database of widgets, things. There's only one thing in the world called widgets, and how much they cost. And that depends on how many you buy. Okay? So this is a database. You ask it, I want to buy so many, how much? So you come in using the predicate buy so many things. What is the cost? That's your question. You can also put in your cost if you like. Okay? And there's a bound. Never mind about the bound that just says you're not going to talk about any money more than this. It also makes it easier for me to program, that's all. So anyway, you want to know, this is a price database. However, in a real situation, prices, the notion of price may be a complex one. It may be the case that you as the storekeeper here, may not be able to derive this price directly because you don't own all the widgets. You get them from all over the place. So notice the predicate in bold product over here, which is simply a database of products held by various suppliers and the prices at which they will sell it. Product, location, and cost. Very trivial. Yeah? The agent that comes into this main server is not interested in the various locations. He just wants to buy and how much. Me, as the seller, because I'm a good seller, I will give you the best possible price. So I want to program this. I know I have access to the database product. At this time, it is not accessible to the customer because he is not interested, right? But I have to compute the price. Now you can see this is a small combinatorial problem. So what I did was, well, I said that the cost is going to be the result of a search. The search is a result of solution, and a solution is defined to be something that meets, that obtains the appropriate number of items. So if you ask me for 10 items, I must give you a solution for 10 items. Furthermore, the search will repeatedly look for the solution until there is no better one found. In fact, because this is a CLP program and not just a product program, I can do branch and bound search. That means I can do intelligent search. I can do efficient search, basically. Right? So in a very short time, really, I will give you the best possible price. Okay? And so that's it, 2 lines. That's all I need to do for branch and bound search. All this is absolutely routine Prolog stuff, okay? Very standard stuff. By the way, just in case you noticed, somebody asked me this. This shriek here is not do nothing. This is Prolog code now, not reactor code. This is a cut. Okay? If you don't know what it is, it's not important. All right. So that's my point here. I'm representing a facet, namely price, based upon some information that I've obtained, and I have to make this connection. Now you can imagine a very much more complicated situation where somebody needs to have sort of a managed view of a complex situation, and I can program this. And yet, there is a very clear notion of why this is a database. I could program this in C, but we will hardly be able to share the information if it were a C program, right? Okay. All right, so I've told you about this idea of programming with a highly structured shared store. I've talked about the reactor. I've sort of tried to justify why programming power in both are very important. You should be able to distribute your programming so that the logic can be distributed. For example, returning to the previous example of optimization, it is possible for people to find the cheapest prices, but each agent would then have to do their own optimization, right? They have to use their own algorithms and do their own search and so on. So I tried to explain that. In the last 5 minutes or so, I thought I would explain one other facet that is of great interest to me, and that issue is the issue of safe concurrent programming. So I'm very interested in programming, in software engineering, where you can have some kind of guarantee that properties that you're interested in are preserved. Okay, so, and I believe that a framework such as OCP is the right framework to start looking at this very basic problem. Okay, so consider the following application. So this won't take long, it's a little involved. Declarative concurrency. The idea is as follows. I am interested in certain program points. In your application, the program points may be in your server or in the agent. This program points marks important events. I'm going to call them E, F, and so on. I'm also going to index these notations E, F with a number denoting the iteration at which that program point is executed. So if it's the 3rd time you're executing it, the program point E, then E3 is the element of interest. Talks about that. The values of all these variables are simply timestamps, just a number. So we'll assume there's a clock that goes 1, 2, 3, and so on. Each time one thing happens, and I want to speak about the values of E1, E2 with respect to F1, and so on. So for example, if I say that E1 is 1, it means that E executed for the first time at time 1. If I say that E1 is less than F1, it means that E must execute before F1 in order for that constraint to be true. Okay? And I can build, and of course, in general, at any given time, there is only a finite number of each event, of iterations of each event that could have happened. So for E, I'm going to let the notation current E just say how many iterations has executed. So this is a very simple arithmetic domain. It embeds a few axioms about time and some other sensibilities that are obvious, but it is essentially a second-order Pressburger formula. Okay, completely formal, and we can do things about it. You can talk about events now, not so unlike using some kind of modal or temporal logic. Okay, you can talk about it using quantifiers, much the same way. So I can talk about these events. Consider now this example, producers, consumers, and look at this piece of code over here. I'm going to denote that this program point is called P for producer, and I'm going to embed a reactor that says softtell, that means augment the solver if you can, the following constraint, current P equals time. So this says a constraint such as P5 equals time, assuming this is the fifth time P is executed. So that's the sort of constraint in hand, and the softtell is a reactor that blocks you until such time this constraint is satisfiable. In exactly the same way, I have another program point here called C for consume, and I talk about the array C, if you like, in exactly the same way. And in the solver, in the server, I keep just 2 lines like this. Right? Sorry, I should have used square brackets rather than subscripts, but the meaning is obvious. I say that for all I, Pi is less than Ci, and for all I, the other stuff. And you can just, if you stare at it for a minute, you can see that what I'm specifying here is a bounded buffer of size 5. Okay? It took me less than 2 dozen characters to say that. Completely formal, second order Pressburger, so in principle, I can guarantee you correctness of bounded buffer in just 2 lines. Okay? And of course, I can do much more than this. Okay? And so the point I was trying to say is that when you have a central store, you are not only talking, the constraints not only specify the relationships between the operations, it also specifies safety conditions, because you cannot proceed unless constraints are satisfiable. If those constraints are well designed, they can talk about correct interleavings and critical safety properties. The problem with this example is I haven't shown you is how do we implement a check for such constraints, but we think we know how. Okay, now, this is the basic idea, I think. Okay. Okay. I'm nearly at the end. This is my second last slide. I'll just show you something that might lead you to believe we can implement everything I've talked about. This is how I think about OCP architecture. The black dots here represent the reactors that are embedded by you in your favorite language. This suggests that you can have more than one reactor in the program. This suggests that your program can be multi-threaded, right? It doesn't matter. So when it's multi-threaded, you can have a choice either in your host language or in the reactor language. I mean, there are sort of ways you can do things. In general, you'll have to manage a set of live reactors, reactors that are still running by some sort of registry here. And in general, the number of reactors is very big for the kinds of applications that I'm talking about. The architecture of the server has as a very key component the notion of triggering, which is not unlike, but very much more advanced than the triggering mechanisms available in active databases. Okay, for those of you who know, active database provided you a way of generating events if certain changes of interest happen to the database. Okay, but these are very low-level programming primitives. It doesn't tell you x is less than 5, okay, or something like this. And so this is something we're building right now. So, and I'm done. I think I'm done. There we go. conclusion. Okay, to conclude, well, I think I've said these points often enough, so thank you very much.